clarity or accuracy, I need to refer to them, perhaps in questions, that sort of thing. I will do that. As the title infers, is an introduction to hydrofracturing in Tennessee. Give you a little bit of background about the oil and gas industry in Tennessee, specific to this discussion topic. By and large, the vast majority of drilling in Tennessee is accomplished through air drilling. But what importance is that? Well, it becomes particularly important when you start talking about how to manage the waste associated with drilling. The other typical option would be mud drilling. There is a fair bit more drilling product that's produced that you have to manage. When you're drilling with air, it reduces the impact that you have to manage there on the site. Two basic geographic areas that we see most of the drilling, the mountainous area, the plateau area, deeper wells, more productive wells. Off the plateau, the wells get shallower, perhaps don't have the longevity of production that some of the other wells do. Gas production in Tennessee is somewhat limited, based in part on lack of the delivery system, lack of infrastructure to move the gas from point A to point B. That's further handicapped by the low price of gas. Basically, if the price were higher, then perhaps the infrastructure would be developed to move that product from point A to point B. Tennessee is a relatively small producer. There doesn't appear to be any boom on the horizon. This gives you an indication, just relatively speaking, of the volume of permits issued over the last 13 years. Kentucky, basically Tennessee represents the bottom line on that graph. I apologize, some of the numbers didn't come up on that graph, but the purpose of the graph is to show Tennessee's level of participation compared to a couple of other local states. Kentucky issuing many more permits. Now, why is that? From my perspective, they're closer to let me go forward one. There's particular areas in the United States that lend themselves to natural gas and oil production. One of the largest of these is the Marcellus Shale in the Northeast. That extends down into Kentucky and Tennessee. And there's some other basin activity, certainly more prevalent in Kentucky than in Tennessee. And that's one of the reasons why you see the numbers skewed toward Kentucky. The United States has large reserves of natural gas, and until recently have not been practical or economical to recover. And as I've said, one of the areas in the Northeast is roughly the size of the country of Greece. However, with the new methods of hydraulic fracturing coupled with horizontal drilling, this gas can be recovered much more practically and much more economically. Fracking is tremendous work, and it encompasses a lot of different activities. It's like trying to say that drilling is one type of drilling. There's a number of types of drillings. There's air drilling, there's mud drilling, there's rotosonic drilling, there's hammer drilling. Fracking, there's a number of different fracking processes as well, all of which include forcing materials under high pressure into, in this case, gas-bearing formations to allow that gas to more easily escape. And I'm in the habit of developing analogies to help me better understand things. And a lot of you may appreciate this. You've got a cedar log that's laying on the floor. It may have a little aroma associated with it. But if you put a number of cuts in that cedar log, you're going to really sense the smell of cedar. You're really going to enhance the ability for that to escape that particular formation. So it's an analogy that sometimes I think helps explain just what this fracturing is doing. It's allowing those gases to more easily escape and thus become producible. Now, horizontal drilling changed the entire approach to this. Historically, we're talking about vertical holes, and they were really prone to missing it or not missing it. Now, if you drill down to a particular formation, and then you can drill horizontally and fracture that unit in a horizontal manner, then it's just, the difference is tremendous. You can affect a much broader area from one particular footprint, drilling down, horizontally drilling in different directions. You can basically access much more of the formation by horizontal drilling than you can just vertical holes in the formation. The activity of fracturing in support of oil and gas production is exempt from the Safe Drinking Water Act in that it doesn't require a UIC permit or an underground injection control permit to inject those substances into the subsurface. Now, the product from that activity, the wastewater from that activity, if it is in itself injected into the subsurface, that would require a UIC permit. But specifically, the oil and gas exploration, fracturing fluids are exempt from the Safe Drinking Water Act. This is a schematic, a very generalized schematic of a completed horizontal well. Some of the specific things that I would point out to you are not so much related to the fracturing itself. What is perhaps more critical is how the wells are constructed. If you look at that first horizon that's indicated there by surface formation, fresh waters, the larger casing, the larger hole will extend down past that, and actually this schematic needs to have an extension down into the Mississippian limestone formation of that outermost casing. That's one of the things that the rules as recently adopted did require, was an extension of 100 feet past any freshwater producing zone. So they've got that exterior casing. After they drill that widest hole, they come back in and concrete that up, particularly around the annular space of the well, between the well casing and the formation. Once that's set, they drill back through that, in the case of this depiction, to around 1,500 to 2,300 feet, at which point they do the same process of cementing that hole back up and then drilling back through that for the purpose of the production casing. Packers tend to isolate the zones, control where the cement goes, also control where the fracture takes place. In this particular depiction, they're targeting the Chattanooga shale, and upon encountering that shale, they begin drilling horizontally. The production packers allow the fracture to be focused within that part of the horizontal well. The packers basically expand and seal off that portion of the well such that your frac will be very specific as to where it takes place. And then move back, expand another packer, fracture another section. Ideally, what this does is provide much more entry of the natural gas back into the production casing and back to the surface. What's extremely critical with respect to hydrofracturing and just drilling and producing in general is the quality of the isolation. What you're attempting to do is to isolate not only this activity from impacting the surface water, but it's equally important for the industry to isolate water from the activity that they're trying to capitalize on down in the formation. So it's not just that the rules attempt to force certain integrity of the well. It's inherent within the industry to have a well of that integrity to protect their investment. Some discussions pertaining to hydrofracking. There had been problems associated with hydrofracking in the Marcellus Shale in Pennsylvania, West Virginia, and Ohio, and perhaps elsewhere, but those we're familiar with. And those, if I'm not mistaken, were the catalyst for the concern expressed by the legislature that I'll get into in another slide or two. Now, to my knowledge, those problems, while not exclusive to well construction and managing wastewater on the surface, they're largely associated with how that return of hydrofracking volume of water was managed on the surface. Perhaps not exclusively, I'm not aware of the extent of those problems. Typically, wells that the industry elects to hydrofrack would involve 1 to 5 million gallons of water per frac. To put that in perspective, Tennessee's largest hydrofracking job to date is 175,000 gallons of water. So why is that the case? Well, in areas where this is more common, you're talking about deeper formations, you're talking about thicker formations, you're talking about higher pressures, all of which require more volume of water. There are problems associated with, particularly in those areas where these frac jobs are so large, with where does that water come from? You know, does it come from a surface stream? Does it come from a water well? That sort of thing. We haven't experienced those problems in Tennessee because basically we don't have those large volume fracking jobs in Tennessee. Wastewater disposal, the water that comes back out to the surface. How do you manage that? That's very complex. As you can imagine, on these large jobs, it's a series of ponds and treatment and discharge, that sort of thing. Again, when we're not dealing with that kind of water, as has historically been the case in Tennessee, we haven't experienced that problem. There are chemical additives and propellants and proppants that are added to this liquid that complement the basic activity is physical fracturing, which the pressure induces that. However, there are other additives and propellants that industry use to complement these fracking jobs. Again, there's problems with leaks and spillage above the ground, and there are certainly fears of aquifer contamination from fracking fluids. As I mentioned, there are no large volume hydraulic fracks in Tennessee to date. The two largest, 172,000, 145,000 gallons of water. And interestingly, as I've been told, both of those were counterproductive in that the water tended to mask or inhibit the ability of the gas to then escape from the very unit that was being targeted. Most of the fracking that's done in Tennessee is done with small volumes of water and nitrogen. Now, I'm not versed in just how that works, but the point being, we don't have the large volume hydraulic fracks. Basically, the methodology in Tennessee has taken a different track. Very low water withdrawal issues. Again, most of the fracking jobs, the ones that have occurred, have been small volume jobs. Nonetheless, there are still public fears about fracturing. The rulemaking process was initiated in 2010, 2011. And it was relatively minor in scope. Some definitions were proposed. We proposed to adjust some bond requirements. We provided some rules for temporary abandonment of wells. During that comment period, however, most of the comments that were expressed were concerns about hydraulic fracturing, even though that wasn't a component of the proposed rule change at that time. House Resolution 98 was passed, which encouraged representatives of TDEC, Tennessee Oil and Gas Association, the League of Women Voters, and the Tennessee Conservation Voters to meet for the purpose of proposing rules to provide for the necessary oversight for the use of hydraulic fracturing as a method of modern natural gas extraction in Tennessee. Commissioner TDEC then committed himself and staff to exploring possible rule changes to address those activities. Resulting changes in the rules. Applications must specify the intent to fracture and if greater than 200,000 gallons of water will be used. Operator must notify TDEC 24 hours prior to fracturing. Operator must have personnel on site during fracturing and backflow. And we added a definition for fracturing in the rules. Keep in mind that prior to this, fracturing wasn't prohibited. In essence, I don't want to say it was not regulated, but it wasn't addressed specifically in the rules. So this rule change has basically encompassed that concept, and I think has done a very good job for establishing the framework, the regulatory oversight framework for fracturing in Tennessee. 30-day public notice and comment period is required for all wells that are proposed to be fractured using greater than 200,000 gallons of water. All new well permits will be posted on TDEC's website. Post-drilling well reports must include the actual volumes used to fracture, the amount and concentration of all the additives used, the amount of wastewater generated, and the method of wastewater disposal. This is specific to all wells. The fracturing data used in wells that use greater than 200,000 gallons of water have to be entered onto a public database referred to as Frac Focus within 60 to 120 days after completion. Trade secret protections are included and are basically beyond the scope of our rules to influence, and some of those do come into play. Other changes to the rules, integrity, and I feel like this is one of the most important ones. Integrity testing on all wells to be fractured, and wells proposed for temporary abandonment. Integrity testing, by and large, done by pressure testing is very important for determining the integrity of that well, to determine whether there's any leaks, to determine whether it is sound. And again, that's not solely a regulatory initiated or supported activity. That's activity that's also critical for the industry to make sure that the wells that they're building have the appropriate integrity so that they can hopefully realize the value of that well. Other changes, again, this applies to wells that are going to be fracked using over 200,000 gallons. If adjoining landowners request that their drinking water wells be sampled, these rules obligate that operator to provide that sampling. The objective of this is that you have some, and quite frankly, most operators are anxious to do this as well because they want to have on record a measure of the quality of water in that water well before they go about doing their drilling and or fracturing. Other parts of the rules prohibit the siting of wells, pits, or storage facilities in wetlands or floodplain areas. There's also some additional minimum specifications for pits and tanks. Other related notes, Bureau of Land Management has proposed fracturing regulations on their land that is similar to Tennessee's rule. Likewise, the Department of Energy published suggestions on states on fracturing that are similar to Tennessee's rule. Currently, EPA is engaged in the study of fracturing issues, which will very likely result in a change in their rules that will then be directed to the states within the next couple of years. That is the extent of that introductory presentation. I'll be happy to field any questions by the board. If I'm not able to answer them, I'll certainly call in somebody that is, or be glad to get back to you. Any members have any questions?
I have a question about the chemicals. Although there's trade secret protections, does somebody within the state know what those are? Like, how is that protected to say that there's not some methyl death going down into the hole and nobody knows about it?
We do require, as part of that disclosure, basically the family of chemicals and the relative concentrations. Now, that allows us to effectively sample to determine if its impact is felt anywhere. Now, also from the perspective of emergency situations, our rules require full disclosure. In other words, worker safety, that sort of thing, that people that are working on the site doing the fracturing, in the event that there's some type of medical emergency or something like that, then they're obligated to fully disclose. I would defer to Alan to agree for the trade secret issue.
That basically
Okay.
covers it. I'll add something to that. Operators that perform these jobs are required, even with trade secret information, to have MSDS sheets that disclose the chemicals that are involved. It just doesn't necessarily disclose the recipe for those chemicals. So those are required, and on Frac Focus, you should be able to see the trade name even if it's a trade secret, correct?
Yes.
So you would be able to look at the MSDS sheets for that.
You're talking about the spillage and water, the contamination. Is there any, what about the technology that's been developed to treat this water or whatever that comes back out before it goes to the streams? Is there anything
Oh, certainly, it's captured and treated on, you know, at least in Tennessee, in the event that there was that type of volume and anticipated discharge, they would be obligated to obtain an NPDES permit for the discharge of that byproduct of that wastewater.
As I understand it, you're drilling a hole in the ground, down and then horizontal. And is the fracturing, does that occur when you put the water and chemicals under pressure and force them against the rock down there and cause the rock to break apart? Is that the way it works?
Yes.
And then, after you've had all that fun, everything starts to come back out the other way?
Mhm.
And does the gas come behind it? I guess it would have to. If the water is under pressure, it would come out first and then the gas would come?
I think that's the technology there to manage that return flow, the return flow being in part the fluid that was used to eject, and also you would expect for there to be some of the product or the gas coming back as well. But your description was correct. You're pressurizing not necessarily the entire well. The purpose of the packers that are expanded in those wells allows that pressurized fracturing event to be very specific. You move back, have the same event again, and they're capable of fracturing multiple zones in a given well. As to exactly how they manage the flow back with the product, I'm not sure. I haven't been standing there when that happens.
I just had this image of some of the 1930s and 40s movies in Texas with the oil coming from the well. Is that kind of what happens?
No, you don't see that anymore.
Okay.
Everything's contained in a pipe, and it either would flow back to a pit or to tanks on location, a line pit, or tanks on location, and that would be disposed of.
Or it stays in the pit.
Right. Well, even the pit would be disposed of unless we got into a situation where there were multiple wells and similar to Pennsylvania, Marcellus Shale,
Pennsylvania
where you
doesn't,
would reuse the fluids.
Pennsylvania doesn't have enough disposal sites, and that's why 1 out of every 150 fracking wells in Pennsylvania is causing a significant ecological impact. And they're only 3 years into their program, which is planned to go over 30 years.
Excuse me, but this is a board.
What is a packer?
Packer, and I'll defer to you, but it's, a packer is, there's various technologies, but it expands and seals against the formation. So if I've got, in this case, a 4.5-inch production pipe going through there and I expand the packer, then basically the annular space between that pipe and the formation is then effectively sealed.
So what's the,
Is it air or what?
No, there are different means of types of packers. The packers used in hydraulic fracturing are permanent packers. They're not meant to be removed. They can be mechanically set, they can be hydraulically set, and they can be hydromechanically set. And they've got sealing elements on there that basically isolate the formation, seal against the rock, just like cement seals the pipe against the rock. So basically they isolate sections of that horizontal well so that the fracks can be directed in each one of what we call stages, what the industry calls stages.
so it's steel, rubber, cement?
Steel, rubber, there's various different, depending on the temperature and pressure, there are different elements involved in the sealing mechanisms of the packers. But the tools themselves are generally steel with some sort of an elastomer type element that seals off against the water. old days, they used to use trees. But they don't do that these days.
So I'm having a hard time imagining how you get something to go down and then out, and then get an expander in a place that you set it. Is it like a grout, you would grout a section of something?
It's expanded, it's a tool and it's expanded. You know, these packers have been developed probably over the last, the current technology has probably been developed over the last 50 years. And they're designed to, with some sort of pressure or mechanical means, compress an element that expands out and seals the formation. And I can get you some more information on that. There's a lot of different varieties. There are companies that only produce packers for the oil and gas industry. That's all they do. And it's fairly technical involved in it. But they've been proven. There's thousands of them been run and they work really well.
My experience with packers is more in the monitoring well industry with collecting environmental samples, and there's some technologies that allow for one well to be drilled in a number of different zones to be isolated within that well and sampled individually. I don't really know how to explain the technology in and of itself, other than to say that it's very effective at isolating movement of liquids, gas, from one part of the formation to another.
I'd say that's right. But basically what you're doing with these things is you're pushing them in the hole on a piece of pipe, and the tool is designed so that the outside of the tool is able to move and expand and push an element to seal off the formation on the outside of the pipe. Does that help a little?
Maybe a picture somewhere.
I think there was a slide that showed what the packers were.
Yeah, but it was not very descriptive. It was just a black line. It didn't really.
But basically, it's to isolate that particular area, so that's the only area that's pressurized.
If you want to go back to that slide, I'll describe that slide. What you got in that scenario, you've got two strings of pipe. The top string of pipe would be set 100 feet below the deepest freshwater formation and cemented back to surface. So you have a piece of pipe in there that has cement that's pumped down the pipe, and the cement comes up and cements the pipe in the hole and isolates that. Then the next string of pipe, same way, pump the cement down the pipe, back up to surface, and that cements that pipe in the hole. The picture that you're seeing in blue, that would be your production casing, and that would be set. There's a packer that isolates the open formation below the cemented pipe. That's the one that says packer at the top. And that's also a permanent packer that's used to seal off. And the same type of packer that would be used in a disposal, class 1 or class 2 disposal well. And that's used to isolate the producing formation from the annulus of that pipe. And then these individual packers down hole, they're all set simultaneously. They're not set individually. So when you pressure up the pipe, the bottom of the pipe is plugged off. When you pressure inside that pipe, you apply pressure, and the elements on those packers expand, and then they shift the sleeve that seals off the port from the inside of the pipe to the packers. And those packers now seal off each one of those individual zones that you would go in and frack. Now, there's also a sleeve in between those packers, and when you frack these in stages, there are different ways of doing this, but generally you drop a series of balls down there, from a small ball to a big one, and they're graduated. So the first ball you drop opens that first sleeve, and you're able to pump out the first sleeve, and you're isolated by the packer from all the remaining sleeves. You typically go from the toe back up the hole, and then you drop a ball and seal those ports off, pressure up and open the next set of ports, and you're able to frack stage 2. And then you continue to drop balls, and you're able to do the same thing as many stages as you want to frack. And this technology, the physics behind this technology was developed a long time ago. This is nothing new. The horizontal drilling process is what's new. The fracturing technology, it's the same fracturing that we've done since 1947 when the first job was done, only with modifications and enhancements and a lot of engineering and science behind it. So if you would look at this from the perspective that if you ran 10 stages, it would basically be similar to drilling 10 vertical wells and fracking 10 vertical wells individually. It's the same thing that's happening. You're not creating, the rock and the physical properties around the rock designate whether or not your frac goes 100 feet or goes 200 feet long. And it's kind of like, if you can picture this formation as all under pressure, the industry does not want to frack out of zone. And you have many, many zones between the zone that you're targeting and the surface water. If you frack out of zone, it's under pressure, you lose your product. You have no asset. So it's in the industry's best interest not to frack out of zone, and that's why they've spent I don't know how many millions of dollars, billions of dollars, trillions of dollars, trying to design and understand how to apply the necessary types of hydraulic fracturing to produce the best, the most gas and fluid out of these wells.
So, in looking at your picture up here, John, looks like there's 1, 2, 3, 4, 5, 6, 7, 8. Is each of those a stage?
Each one of those would be a stage.
Okay, so you could drill 8 different wells down from the surface. This way you're doing it one time.
That's right.
Which looks like it has less likelihood of impacting on any kind of waters if you rather than drilling 8 different wells down through the water table.
It's physically impossible, and I have to say, if Albert Einstein were alive today, he'd be rolling over in his, to hear that you can frack from down below to surface. As you get closer to surface, you have a change in stresses, and those changes in stresses cause the frac from going vertically to turning horizontal in what's called a pancake frac. And that's probably the least productive frac that you can get in the industry. That's the worst type of frac you can have, is to have a frac roll over and be a pancake frac. So what you're doing is and the reason that happens is because at about 1,000 feet, your surface stresses change. And a frac grows perpendicular to what's called the least principal stress. And the easiest way I can explain that is if I'm standing on that book right there, the most stress on that book is from the top down. So as you get closer to surface, the weight of the ground, the weight of the rock on top of your producing formation lightens, it lessens. And the science behind this is about 1,000 feet from surface, and that varies depending on your geology and where you are. But as you get closer to 1,000 feet from surface, your fracs tend to roll horizontal, and they can no longer go vertical. And on top of that, in between most of these freshwater formations, you have coal. And coal naturally has methane gas in it. So you would have to be able to frack through all of these formations, through the coal, and into the freshwater zone, the contaminated freshwater zone. And scientifically, that's very difficult. And it's not in any industry's best interest to do that, because then they lose their product. Because their product's under much greater pressure down below the ground than it is closer to the surface.
And I would add to that, on the comment about achieving that with 8 different wells, that's a concern as well, because the impact on the surface from 8 different drilling operations, roads going to it, pits dug and all that sort of thing, that impact is tremendously greater than what this technology provides for now. I mean, this technology allows for better explore, better capture the product in that formation than an equal number of vertical wells. Not only down below, but the impact up top is remarkably less. And here the depiction is going that way. Well, that formation is 3-dimensional. You might move over 15, 20 feet, drill another one, and go that way, and go that way, and go that way, and your impact on the surface is remarkably less than going all around that lease and popping wells in.
That's right. And I might also add, this is not new technology. There are thousands of publications about hydraulic fracturing that the industry has. It's very well known, the science and technology behind hydraulic fracturing. And if you want more information on it, ask somebody in the business.